Right, optical isomerism. Tell me, optical isomerism. So what is optical isomerism? What are optical isomers? Organic compounds having same molecular formula but different spatial arrangement of atoms or group of atom on asymmetric carbon, called optical isomers, phenomena called optical isomerism, right? In optical isomerism we have some important terms. First one, plane polarized light. So what is a plane polarized light? So generally ordinary light oscillate in all possible directions perpendicular to the direction of the propagation. When ordinary light is passed through the Nicol prism, so vibrations are adjusted in only one plane, which is called PPL, plane polarized light. The light whose vibrations occurs only in one plane is called plane polarized light. Okay, next is optical activity, optically active compounds. What are optical activity? It is a property of the substance to rotate the PPL to either right side or left side, called optical activity. And what are optically active substance? Tell me, the substance which can rotate the plane polarized light either right side clockwise direction or anti-clockwise direction, that is left side, called optically active substance. That is also completed. Next is optical inactive substance, also completed now, right? What are optically inactive substance? The organic substance which do not have interaction with plane polarized light, called optically inactive substance. Till here completed, right? Okay, next, right? Chiral carbon, continuation. Chiral carbon or asymmetric carbon. Asymmetric carbon, or it is also called chiral center or stereo center, etc. Tell me, what is a chiral carbon? So chiral carbon, asymmetric carbon is the carbon atom which is attached to 4 different atoms or 4 different groups, called chiral carbon or asymmetric carbon. For example, let us take carbon atom attached to 4 different atoms or groups. Let us take A, B, C, D, right? Therefore, now this carbon atom attached to A, B, C, D, 4 different groups, it may be atoms, then this carbon is called chiral carbon or asymmetric carbon. Therefore, chiral carbon, asymmetric carbon is the carbon atom which is attached to 4 different atoms, it may be 4 different groups, right? Next, for example, let us take CH3, CH, OH, COOH. Tell me, is this molecule has chiral carbon? Yes, here now it is first carbon, second carbon, third carbon. Which carbon is a chiral carbon? Second carbon, because on second carbon there is a hydrogen, OH, COH and methyl. There are 4 different groups present on this second carbon, therefore it is a chiral carbon, chiral center, right? Like that, identification of molecule is important. Question is like this: which of the following molecule has chiral carbon, asymmetric carbon? Option will be there. Most of the time they will give the IUPAC names. By giving IUPAC name, they may expect which is chiral carbon, which is not having chiral carbon. Next question. Then, if molecule has at least one chiral carbon, it is generally optically active. But there are some exceptions also. But in general, if molecule has at least one chiral carbon, it is optically active. Therefore, questions also like this: which of the following is optically active? So, if they ask optical active, we need to identify the which of the following given molecule has chiral carbon. Okay, this kind of question can be expected. Write down: chiral carbon, asymmetric carbon. The carbon atom which is attached to 4 different atoms or groups. 4 different atoms or groups called chiral carbon over our asymmetric carbon. Chiral carbon or asymmetric carbon. Next point. Molecules having at least one asymmetric carbon. Molecules having at least one asymmetric carbon can exhibit optical isomerism. Optical isomerism. Take example. This is called lactic acid. Lactic acid. Next, CH3, CHCl, CH2, CH3. Can it exhibit optical isomerism? Yes, there is a one chiral carbon, asymmetric carbon. It can also exhibit optical isomerism. Next, can it exhibit optical isomerism? So this carbon can exhibit because there is one hydrogen, one side hydrogen. No. Now okay. One side is hydrogen, methyl. Okay. It is a chloroethyl, just ethyl. Right? Can exhibit optical isomerism. Write down question. Which of the following molecule can exhibit optical isomerism? Which of the following molecule can exhibit optical isomerism? 2-chloro pentane 2 3 4 all. Tell me which of the following can exhibit optical isomerism. So for optical isomerism, what is the condition? Molecule should have chiral carbon. Okay, see, chiral carbon is not a 100% criteria. There are some exception, but in generally, if molecule has one chiral carbon, remember, if molecule has only one chiral carbon, it is 100% optically active. So therefore, now tell me 2-chloropentane. So pentane, how many carbon atoms? There are 5 carbon atom, and chlorine on second carbon atom. Here hydrogen will be there. Tell me. So this is a one propyl group, methyl group, hydrogen, chlorine. So it can exhibit optical isomerism because there is a one chiral carbon. Then what about it is like ammonium ion, right? So it is a methyl, ethyl, propyl, hydrogen, and there is a positive charge. So remember, so if nitrogen atom attached to 4 different groups, of course having positive charge, can also be exhibit optical isomerism. It is like carbon, it can also exhibit optical isomerism, therefore it is also possible. Next is carbon having like hydrogen, deuterium, tritium. Okay, tell me, hydrogen, deuterium, tritium, all three are actually isotopes. So therefore, if the isotopes are present on carbon atom, they can also make optical activity. So therefore, hydrogen, different, deuterium is different, tritium also different, methyl different. It can also exhibit optical isomerism. It means If there are isotopes, they can also form they can also exhibit what? Optical isomerism. Answer is all. Okay. So therefore, so two example important. Next is optical activity. No, optically active compounds or no. Next, right? Asymmetric molecule. Asymmetric molecule or chiral molecule or disymmetric molecule. So what are asymmetric molecule, chiral molecule or disymmetric molecule? Tell me. Now we have studied what is a chiral carbon or asymmetric carbon. What is a chiral carbon? The carbon atom which is attached to 4 different atoms or group is chiral carbon, right? Then now what is asymmetric molecule, chiral molecule? Asymmetric molecule, chiral molecule is the molecule which is having chirality, right? The molecule which is having chirality. So what is the meaning of chirality? If the molecule do not have 3 elements of symmetry, that is plane of symmetry, center of symmetry, alternating axis of symmetry. If any molecule do not have these 3 elements of symmetry, then that molecule is called a chiral molecule or asymmetric molecule, right? So therefore, tell me now, what is a chiral molecule? The molecule which do not have 3 elements of symmetry. What are the 3 elements of symmetry? 1. Plane of symmetry. Plane of symmetry. B. Center of symmetry. And 3. Alternate axis of symmetry. If any molecule do not have these 3 elements of symmetry, that molecule is called asymmetric molecule or chiral molecule. Then what is the importance of this asymmetric molecule, chiral molecule? See, if any molecule is asymmetric or chiral, it 100% it is a what? Optically active. Therefore, for optical activity, what is the condition? The condition for optical activity is not a chiral carbon. The 100% criteria is what? Chirality or asymmetric molecule. The molecule which is not having these 3 elements of symmetry, which is called asymmetric molecule. Then if the molecule is asymmetric, it is 100% chiral molecule or optically active. Therefore, the condition for optical activity is a chirality but not chiral carbon. What is the meaning of this? See, if any molecule having chiral carbon, chiral center, it is optically active. Sometimes it is optically inactive also. Sometimes it is optically inactive. For example, let us take best example is tartaric acid. Right. This is a tartaric acid. This tartaric acid has 2 chiral carbon. This is 1 chiral carbon. It is another chiral carbon. Even though this tartaric acid has 2 chiral carbon, it is optically inactive. It is due to presence of what? Plane of symmetry. Very good. Plane of symmetry. It means this tartaric acid can be divided exactly 2 half, upper part and lower part. Both are actually mirror images of each other. This molecule has plane of symmetry. Therefore, it is not a chiral molecule. Right? It is not a chiral molecule, and moreover, it is called mesotartaric acid. Mesotartaric acid. Therefore, mesotartaric acid has 2 chiral carbon but optically inactive. Why? Because it do not have chirality. It do not have chirality. It means it has, when the molecule has chirality, if the molecule do not have these 3 element of symmetry, it has, this molecule has which element of symmetry? Plane of symmetry. Therefore, it is a achiral molecule, or what is a asymmetric, symmetric molecule or achiral molecule. Right? That means, so For optical activity, what is the condition, what is the criteria? Chirality is a criteria but not chiral carbon, chiral center. But if any molecule having one chiral carbon, only one chiral carbon, it is 100% optically active. If molecule has two or more chiral carbon, it may be optically active, it may be optically inactive. Then how to identify optically active, optically inactive? It is presence of what? These three elements of symmetry. Now let's see what is the meaning of these three elements of symmetry. First one, plane of symmetry. So what is a plane of symmetry? Plane of symmetry is, it is an imaginary plane which divides the molecule into two equal halves such that one half of the molecule is a mirror image of another half. It is imaginary plane. An imaginary plane which divides the molecule into what? Two equal half. It must divide the molecule into two equal half, and those two halves are mirror images of other. See, you just imagine here, you divide these two, it becomes half of exactly, and this lower, no, the lower half is there, no, this is exactly mirror image of upper half is mirror image of lower half. Then this molecule is said to be how? Plane of symmetry. ಈ ಥರ ಇದ್ದರೆ molecule, then we used to say that molecule has plane of symmetry, right? So therefore, what is a plane of symmetry? An imaginary plane which divides the molecule into two equal halves such that one half of the molecule is mirror image of another half. Next, center of symmetry. So what is a center of symmetry? For center of symmetry, let us take this example. It is a cyclobutane. In cyclobutane, let us take groups are methyl hydrogen, here methyl hydrogen, chlorine H. Okay, center of symmetry is, it is imaginary axis. The imaginary axis which passes through the center, let us take, there is an imaginary axis which passes through the center. When imaginary axis passes through the center, two identical groups are, okay, now two identical groups should be present same distance from the center, like H. Here the methyl, they must be present same distance from the center. Even chlorine also comes same. Okay, imagine it is like this, chlorine up here, chlorine down here. Therefore these two chlorine also comes, means from the center they are actually same distance. This molecule said to have center of symmetry. So when the molecule has center of symmetry, an imaginary plane, an imaginary axis which, or imaginary line which passes through the center, and the identical group must be connected, where identical group must be placed or must be present same distance from the center, like from center to methyl, same distance, chlorine, hydrogen, same distance. Then this molecule said to have center of symmetry. If the molecule has center of symmetry, it is not optically active. See, if molecule has at least any one of this element of symmetry, that molecule do not have what? Optical activity. Next, that is center of symmetry. Next is alternating axis of symmetry. Alternating axis of symmetry is, like for example, you take cyclobutane. Okay. Now when molecule is rotated, okay, rotated by n degrees, you can rotate like 90 degrees, 180 degrees. So on rotating 180 degrees, suppose if you able to get the same structure like this, then this molecule said to be have got alternating axis. See, if you rotate triangle, okay, it is a propane, cyclopropane. If you rotate cyclopropane even in 120 degree like this, rotate 120 degree like this, you will get in every 120 degrees you will get same structure or not? Next, or triangle, you rotate like this, every 180 degrees you will get same structure. right? If molecule able to get same structure on rotating in not only one direction, in many direction, then that molecule said to have alternating axis of symmetry. Okay, then now question is, for us we will get question like this: which of the following optically active, which is optically inactive? Iste question baradu. Then if molecule given and they asked which is optically inactive, optically active, then how to see all this? Most of the time the question will come plane of symmetry. Okay, in very rare case question comes on this. Question on this, no. If it is optical inactive, you will get here only, maximum here only. Very few molecules are there like this. You need not to bother about this. ಈ ಎರಡೆಲ್ಲ ಕ್ವಶನ್ ಆನ್ಸರ್ ಸಿಗ್ಬಿಡುತ್ತೆ, ವೆದರ್ ಆಪ್ಟಿಕಲ್ ಆಕ್ಟಿವ್, ಆಪ್ಟಿಕಲ್ ಇನ್ಆಕ್ಟಿವ್ ಅಂತ, ರೈಟ್? ಸೊ ದೇರ್ ಫಾರ್ ದಿಸ್ ಈಸ್ ನೆಕ್ಸ್ಟ್ ಈಸ್ ಕಂಡೀಷನ್ ಫಾರ್ ಆಪ್ಟಿಕಲ್ ಆಕ್ಟಿವಿಟಿ. ಟೆಲ್ ಮಿ, ವಾಟ್ ಈಸ್ ದ ಕಂಡೀಷನ್ ಫಾರ್ ದ ಆಪ್ಟಿಕಲ್ ಆಕ್ಟಿವಿಟಿ? ಮಾಲಿಕ್ಯೂಲ್ ಮಸ್ಟ್ ಬಿ what? Asymmetric. Molecule must be asymmetric or molecule must be chiral. Okay, but is it chiral carbon is 100% criteria? No. We have seen here mesotartaric acid has 2 chiral carbon but is optically inactive. Okay, next we have enantiomers and diastereomers. Okay, right till here this is written, no? Next, right, asymmetric carbon, asymmetric molecule, chiral molecule, asymmetric or chiral molecule. Okay, done. Right, the molecule which do not contain, the molecule which do not contain 3 elements of symmetry, the molecule which do not contain 3 elements of symmetry, called asymmetric molecule or chiral molecule. What are the 3 elements of symmetry? Take this: A, plane of symmetry; B, center of symmetry; C, alternate axis of symmetry. Plane of symmetry, center of symmetry, alternate axis of symmetry. Next, right, plane of symmetry. Plane of symmetry, an imaginary plane which divide the molecule into, an imaginary plane which divide the molecule into 2 equal half such that one half of the molecule is 2 equal half, such that one half of the molecule is mirror image of, one half of the molecule is mirror image of another half called plane of symmetry, called plane of symmetry. Okay, so take example, mesotartaric acid has plane of symmetry, therefore it is optically inactive. Next, alternate axis of symmetry. Alternate axis of, no, second one, no, center of symmetry, right? Second one, center of symmetry. Done. A molecule said to have center of symmetry, a molecule said to have center of symmetry if all straight line that can be drawn through the center of molecule meet the identical atoms at the same distance from the center. Meet the identical atoms at the same distance from the center. Okay, example, take example. Next, alternating axis of symmetry. A molecule said to have alternating axis of symmetry. If molecule is rotated through imaginary axis, if the molecule is rotated through the imaginary axis by 360 degrees, if it gives identical structures, okay. Example, cyclopropane, cyclobutane. Even cyclobutane also rotated the molecule, this molecule, by 360 degrees. You will get the identical structures, no? Because for every 90 degrees, no? It is like a cube, no? For every 90 degrees you will get identical structure. If you get identical structure by rotating the molecule certain degrees, then which is having alternating axis of symmetry. Okay, next point, right? If the molecule contain any one of these element of symmetry, which is optically inactive, okay. Next, right, based on chirality, molecules or organic compounds are classified into three types. Based on chirality, organic compounds are classified into three types. One, dextrorotatory, levorotatory, racemic, mixture over our rhythmic modification. Okay, right. So based on optical activity, organic compounds are classified into dextro, levo, rhythmic mixture, rhythmic modification. Tell me, what is dextro-rotatory? The isomer which can rotate the plane polarized light towards right side, right? Towards right side is nothing but clockwise direction, called dextro-rotatory. It is denoted by small letter d or plus. Okay, small d only. Similarly, the isomer or the optical isomer which can rotate the plane polarized light towards left side over r, which is called minus, called levo-rotatory. But important is rhythmic mixture. What is rhythmic mixture? The equimolar mixture of dextro and levo-rotatory, 50% D, 50% L, is called rhythmic mixture. That is, equimolar mixture of D and L is called rhythmic mixture, which is denoted by DL or plus or minus. Then rhythmic mixture, see, rhythmic mixture is optically inactive. That means if PPL is passed through the rhythmic mixture, it neither rotate, means right and left side, right? It is optically inactive. See, it is optically inactive. It is not mean that it cannot rotate PPL to right and left side. So it is optically inactive because it contains D and L, right? So D rotate the PPL to right side, something x degrees. Then L also rotate the PPL to left side, same x degrees. Then the resulting rotation become 0, which is called external compensation, right? Externally, one rotate PPL to right side, other rotate PPL to left side, both mutually cancelled, but it looks like it is not rotating, PPL to any side, but actually it can rotate PPL to left and right side same extent. The resulting rotation becomes 0, which is called external compensation, right? Therefore, rhythmic mixture is optically inactive due to external compensation. Okay, next we will study two more important terms here, resolution and racemization. One is a racemization. So what is a racemization? So racemization is, let us take, we have D or let us take L, right? D is a optically active, L also optically active. Now if you convert D or L into DL, racemic mixture, which is called racemization, right? Racemization nothing but the process of conversion of optically active either D or L into racemic mixture. Take any one D form or L form, you just convert into DL form, which is racemization. Therefore, in racemization, optically active compound get converted into optically inactive compound because racemic mixture is optically inactive. Next, there is another important term, resolution. Resolution is quite opposite. Now let us take, we have DL form, which is optically inactive. Then convert DL into either D form or L form. The process of separation of D and L from racemic mixture, isn't it? It is nothing but separation, no? The process of separation of D and L from the racemic mixture is called resolution. In resolution, optically inactive compound converts into optically active compound. Optically inactive. So optically inactive compound converts into optically active. See, it is called optically inactive. The resultant rotation becomes 0. Now, if you take DL form in polarimeter, okay. So take the DL mixture in polarimeter, right? Keep in polarimeter. Then tell me what polarimeter shows. reading? 0. Polarimeter show the reading is 0. Like optical inactive compound, based on that only it is optical inactive, right? So because the resultant rotation becomes 0, right? If you separate D and L, it is optically active. D is optically active, L is optically active. So therefore the separation of D and L from the racemic mixture is called a resolution. Okay. So next we have enantiomer and diastereomer. Okay, write down. Dextrorotatory. Right, dextrorotatory. Right, the isomer, the optically active isomer, which can rotate plane polarized light, towards right side or clockwise direction, called dextrorotatory. It is denoted by small d, not capital D. Capital D is different. Small d or plus. Next, levorotatory. The optically active isomer which can rotate PPL2, plane polarized light towards left side, anti-clockwise direction, called levorotatory. It is denoted by small letter L or minus. Next, racemic mixture. Or racemic modification. The equimolar mixture of dextro and levorotatory called racemic mixture or racemic modification. Racemic mixture or racemic modification. It is denoted by DL or plus or minus. Racemic mixture is optically inactive. Due to external compensation. Optically inactive due to external compensation. Next, racemization. The process of conversion of optically active compound in bracket D over L. The process of conversion of optically active compound D or L to form what? Racemic mixture. DL2 racemic mixture. D or L2 racemic mixture called Racemization, called racemization. D over R L gives rise to DL. Next, resolution. Resolution. The process of separation of D and L from the process of separation of D and L from racemic mixture. Called resolution. Called resolution. Okay. Now let's see. Now we understood that dextrorotatory. What is the dextrorotatory? The isomer which can rotate PPL to right side, dextro, and the isomer which can rotate PPL to left side is levo. For example, glucose. Tell me, we have studied glucose is a dextrorotatory, whereas fructose is a levorotatory. It means fructose can rotate PPL to left side. How many degrees? We have studied we have studied specific rotation. What is the specific rotation of fructose? Minus 92.4. And what is the glucose can rotate PPL to right side. What is its specific rotation? Plus 52.5. 4 or 5? Okay, 4 or 5. Fine. It means, then tell me, see, glucose can rotate PPL to right side, fructose left side, and what about mannose and galactose? They can also rotate PPL to right side. It means, is it all the compound can rotate plain polarized right side same extent? Same extent of rotation? No. It means different organic compounds can have different extent of rotation. It may be right side, it may be left side. Then now point is, extent of rotation depends on what? And how do you calculate or how do you measure the extent of rotation? So extent of rotation can be measured by polarimeter, and moreover it is purely experimental value. You cannot tell by seeing the molecule. If I write the one structure, is it dextro or levo? Don't know. So polarimeter has to say, right? So take the solution, keep in polarimeter, so that polarimeter give the value. Therefore this is a completely experimental value, not theoretical value. Next point. Then extent of rotation depends on which factor? So the extent of rotation depends on, one, nature of the substance, two, it also depends on nature of solvent. Which solvent you have taken? Either you have taken water or alcohol or any other solvent. Two, extent of rotation also depends on concentration of the solution. Concentration of solution. The concentration must be gram per milliliter. 4, extent of rotation also depends on the wavelength of the light taken, because in polarimeter we take the monochromatic light. No, the meaning of monochromatic light is only one wavelength. We take the only one wavelength light. Okay, that is passed through the Nicol prism, which gives PPL, plain polarized light. Therefore that wavelength also decides what extent of rotation. That's what wavelength of light is used. 5, even extent of rotation also depends on the length of the solution, because in polarimeter we take the test tube, right? And what is the length of the test tube? Nothing but length of the solution. So it is also depends on length of a solution, which usually in decimeter we take, because 1 dm decimeter equal to 10 centimeter. Next, last one is temperature. It is also depends on temperature. Therefore which of the following factor now affect the extent of rotation? All these 6 factors affect the extent of rotation. Then when these many factors affect the extent of rotation, then how do you calculate rotation? Therefore we use the term called specific rotation. Then what is the specific rotation? In specific rotation, in the sense specific condition, no, the rotation can be measured in specific condition. Let us take a polarimeter. Okay, so polarimeter, there will be a test tube, right, and through polarimeter there will be a monochromatic light will be passed through the this solution. It is an instrument, there is a big instrument, we cannot draw it, right. So therefore when monochromatic light is passed through this, okay, then this polarimeter measures the rotation, whether it is rotated left side, right side, and if it is right side, how many degrees, left side, how many degrees. Okay, that's what to measure this we take the specific rotation. So what is the specific rotation, not conductance? Okay, specific rotation. Now what is the specific rotation? in specific condition, what are the specific condition? Condition 1, temperature is constant, at constant temperature, and at given wavelength also be given particular wavelength, lambda, that is also given wavelength, but the length of the solution must be, it is 1 dm or 10 centimeter, right. To measure the rotation we take the length of the test tube, nothing but length of the solution 1 decimeter, 10 centimeter, and concentration also be a constant, it is a 1 gram per milliliter. Therefore now you can define what is a specific rotation. The rotation produced by the solution, right, the rotation produced by the solution containing 1 gram per ml concentration, 1 decimeter length of the solution at given wavelength and given temperature. See, in this specific condition you allow the passage of light, monochromatic light, which give the rotation, no. So that rotation is called what? Specific rotation. Then how do you define specific rotation? So by using all these terms. The rotation produced by the solution, which solution? Solution must be gram per milliliter, and what concentration, what length? 1 decimeter or 10 centimeter length of the solution at given temperature, given wavelength. Temperature and wavelengths are particularly mentioned, which is called specific rotation. This specific rotation denoted by alpha degree Celsius, here is lambda wavelength, is equals to, it is a alpha observed, it is called observed rotation into L into C, where what is alpha observed equal to observed rotation, L equal to length of solution, it should be in decimeter, C equal to concentration of solution, it must be gram per ml. It is a specific rotation and formula to calculate specific rotation. Okay, done. The extent of rotation of plane polarized light, the extent of rotation of plane polarized light depends on following factors. Depends on following factors. and it is measured by, not written, nature of substance, nature of solvent, concentration of solution, gram per ml, wavelength of light used, length of the solution decimeter, temperature. Next point, the rotation of plane polarized light, the rotation of a plane polarized light measured by, the rotation of a plane polarized light measured by polarimeter, measured by polarimeter. Next, right, specific rotation, specific rotation, the rotation produced by the rotation produced by the solution containing solution containing 1 gram per ml concentration, 1 gram per ml concentration, comma 1 decimeter length of the solution, 1 decimeter length of solution for a given wavelength of light, for a given wavelength of light and given temperature, for a given wavelength of light and given temperature, called specific rotation, called specific rotation. So take formula. Alpha degree Celsius and lambda equal to alpha observed divided by L into C. So this weekend syllabus is complete isomerism, full isomerism and F block elements. Okay, previous question also become organic chemistry. You need not to stick on only one concept. Previous question comes, you have to study previous questions, previous topics. Right, enantiomers. Next, enantiomers, diastereomers. So what are enantiomers and diastereomers? Tell me. Enantiomer is non-superimposable mirror images, right? A non-superimposable but they should be mirror images. So non-superimposable mirror images are called enantiomers. What is the meaning of this? For example, you take lactic acid. Lactic acid is CH3 COOH OH, it is H. It is called D-lactic acid, small d. D-lactic acid. Tell me, its mirror image is what? Okay, if you keep the mirror here, you can get a structure like this. COOH is here, CH3 OH, and this is H. Okay, then this is a L-lactic acid. Okay, therefore D-lactic acid, L-lactic acid, both are what? They are actually mirror images. See, if you keep the mirror for this, you can get this, right? These two are the mirror images, but they are actually not superimposable. See, superimposable means you pick the molecule and keep here. Now all the atoms should be superimposed. Now tell me, if you pick and keep here, which superimpose? Methyl superimpose, methyl, and carboxylic group superimpose. Then what about OH group? This OH group here, this OH come here. That means OH group and H group, these two are non-superimposable. It means the whole molecule is not superimposable. Therefore, now which is called what? D and L forms are enantiomers. Right? So you can also take like this. Our right hand, left hand. The relation between right hand, left hand is enantiomer only. Okay. If I show my right hand on mirror, I can see like this. Left hand, tane? Right? Show your right hand on mirror, left hand kanutte. So therefore, it is mirror, right? So our right hand, left hand, both are, they are enantiomers. Right? So they are actually non-superimposable, no? See, you bring like this, these two. Can they superimpose? Either tarbadre. Opposite barbadar. Right? You bring like this only, right? So they are actually non-superimposable. They are non-superimposable, but they are mirror images. Therefore, so right hand, left hand relation is enantiomeric relation. These two are enantiomers, like lactic acid and L-lactic acid, D-lactic acid, they are enantiomers. Okay, fine. Now, what is the characteristics of enantiomer? One, see, D and L form, D and L relation always enantiomers. Therefore, enantiomers will have same physical property, even identical chemical property, but they differ in rotation of plane polarized light. One can rotate PPL to right side. See, this D can rotate hydrogen to, no, rotation is always seen from hydrogen to OH. Right side, no. H to OH, right side. H to OH, left side. So therefore, one can rotate PPL to right side, another can rotate PPL to left side. But they have similar physical property, even identical, not exactly similar, but identical chemical properties. So they differ only in rotation of plane polarized light. That is enantiomers. Next is diastereomers. So diastereomers, see, diastereomers are, these are also non-superimposable. Non-superimposable in and non-mirror images. They actually mirror images, here non-mirror images. Therefore, non-superimposable and non-mirror images. So non-superimposable, non-mirror images are called diastereomers. Okay, let us take one example. CH3, CHCl, CHBr, CH3. If I write the structure CH3, CH3 and chlorine, this chlorine H, bromine H. Okay, tell me, take this is a structure 1. What's the mirror image? CH3 comes on same. Okay, chlorine right side, it comes left side, HH, structure 2. Tell me, structure 1, structure 2, both are what? Enantiomers. I'll write the same molecular formula, another structure. Methyl group, that will be same, I do not change. I'll change the I'll keep chlorine also same and H also same. I'll change Br position. Take structure 3. Now tell me, structure 3, it is also having same molecular formula like first and second. Now tell me, what is the relation between 1 and 3? Whether they are enantiomer? They are not enantiomer, because enantiomers are non-superimposable. They should be mirror images. 1 and 3 is not they are not mirror image. Therefore, they are 1 and 3 are what? Non-superimposable and non-mirror images. They are diastereomer. I'll write another structure for this. Take chlorine, hydrogen, here is hydrogen, here is Br. Take structure 4. Then what is the relation between 1 and, now tell me, first is 1 and 2 are what? 1 and 2 are enantiomers, and 3 and 4 are what? They are also enantiomers, because non-superimposable mirror images. So these two are also enantiomers. But now I want the relation between 1 and 3. 1 and 3, 1 3 and 1 4. Okay, comma 2 3, 2 and 4. All these are diastereomer. They are non-superimposable, non-mirror images. They are called diastereomer. Okay, even the relation between cis and trans also diastereomers. For example, let us take cis dichloro 1 comma 2 dichloroethene. Take its its cis form. So chlorine and HH. Can you tell me these two are whether they are non-superimposable or not? They are non-superimposable. Whether they are mirror images? No, they are not mirror images. Therefore, non-superimposable mirror images. Therefore, cis-trans relation is always diastereomeric relation. DL, small d, small l, always enantiomeric relation. So, therefore, if this is a D, you will get L. If this is a L, you will get D. Which is D, which is L? We don't know. That polarimeter has to decide. Ashatane, small d, small l value you can't tell, I can't tell. By seeing structure, it is not predicted. Then you may have doubt. You written, sir? You have written here somewhere? You may ask. Ali bardiralla sir matte ನೀವು DL ಅಂತ. ಇದು ಒಂದು molecule ಬರ್ದಿನಿ ನಾನು. Okay. This one molecule, it is textbook, it is mentioned that D form. Rotation is dextro. OH is right side ಇರಬೇಕು, H ಈ ಕಡೆ ಇರಬೇಕು, ಅದು ಡೆಕ್ಸ್ಟ್ರೋ ಬರುತ್ತೆ ಅಂತ. ಹಾಗಾಗಿ ಬರ್ದಿನಿ ಅಷ್ಟೇ. ಎಲ್ಲಕ್ಕೆ ಇದೇ ಥರ ಮಾಡಬೇಡ್ರಿ. ಒಂದು ಲೈನ್ ಥರ ಹೊಡೆದು ಡೆಕ್ಸ್ಟ್ರೋ ಲೆವೋ ಅಂತ ಬರಲ್ಲ. Right? So, this is how dextro and that is enantiomer and diastereomer. Written. Enantiomers, non-superimposable mirror images are called enantiomers. Non-superimposable mirror images are called enantiomers. Next point, the fundamental criteria for enantiomerism, the fundamental criteria for enantiomerism is chirality, but not chiral carbon. The fundamental criteria for enantiomerism is chirality, but not chiral carbon. Next point, enantiomers have identical property. Enantiomers have identical property, but they differ in rotation of plane polarized light, but they differ in rotation of plane polarized light. Next point, the relation between small d small l is always which relation? Enantiomeric relation, right? So like brother sisters, d small l, they are always enantiomeric relation. Okay, take example, d lactic acid, l lactic acid. Next, diastereomer. Diastereomer, non-superimposable, non-superimposable, non-mirror images are called non-superimposable, non-mirror images are called diastereomers, Okay, take example, okay, optical isomerism in lactic acid. Take down. Optical isomerism in lactic acid. Now tell me whether lactic acid is optically active or optically inactive. Optically active. How do you say that it is optically active? It has chiral carbon. Is it chiral carbon is a criteria for optical activity? No. Even though chiral carbon is a not criteria for optical activity, but if molecule has one chiral carbon, it is 100% optically active. Because if molecule has one chiral carbon, there is no meso compound. If molecule has two or more chiral carbon, there is a possibility of meso compound. Meso compounds are optically inactive. That's what meso here, no chance. That's what if there is a one chiral carbon, you can take it is optically active. Therefore, it is optically active. Now let me write this structure. The structure of lactic acid is like this: methyl group and COOH. Take down. It is OH is one side, H is another side. Now this carbon is a chiral carbon. Now, so generally the rotation will be observed from hydrogen to OH. Okay, tell me. So when you take the rotation from hydrogen to OH, which is called small d lactic acid, then capital D is different. That is, we have studied carbohydrate. Okay, yeah, that we will study next class. What is capital D? Next, write its mirror image. So here rotation is again hydrogen to OH, which is called L lactic acid. So D lactic acid, L lactic acid, these two are the enantiomers. Then what about a racemic mixture? Let it be. Racemic mixture is, so yeah, so you can take, it is a 50% D and 50% L, right? Therefore, no, this composition is called racemic mixture. Next, optical isomerism in tartaric acid. Take down. Optical isomerism in tartaric acid. In tartaric acid, there are two carboxyl group and two OH group will be there, like this. Okay. Then there are how many symmetric carbon? There are two asymmetric carbons. Okay, right. Now let us write the structure of tartaric acid. COOH, COOH, OH, H, OH and H. Tell me whether it is a D tartaric acid or L tartaric. No, one second. No, wait. I'll write OH here, H here. Tell me whether it is a D or L tartaric acid. So the rotation will be observed from hydrogen to OH and hydrogen to OH. Then you see the overall rotation either clockwise or anti-clockwise. It is a clockwise. Therefore, it is a D tartaric acid. So will you write its mirror image? To write mirror image, you need not to keep mirror. ಅಷ್ಟೇ ತಾನೆ? ಅಲ್ಲ, ಮಿರರ್ ಇಮೇಜ್ ಬರಂದ ತಕ್ಷಣ ಮಿರರ್ ಇಲ್ಲ ಅಂತ ಹೇಳ್ಬೇಡ್ರಿ. Right? It is a L lactic acid. Sorry, L tartaric acid. L tartaric acid. ಹೇಳಿ. ಪ್ಲೇನ್ ಸಿಮೆಟ್ರಿ ಅದನ್ನೇ ಇಲ್ಲಿ ಬರುತ್ತಾ? ಹೆಂಗೆ ಬರುತ್ತೆ ನೋಡ್ರಿ. ಎರಡು ಡಿವೈಡ್ ಮಾಡಿರಿ. Divide these two, it means plane. So you will get two equal. Is it you will get two equal half? Two equal half barutte. But whether they are mirror images to each other? No. So there is another molecule COOH. Here two OH groups are same. same side of the chiral carbon. Now you can divide this molecule into two equal half. Okay, you can divide two equal half, and each half is a mirror image of another, right? Like upper half, the mirror image of lower half. This is also mirror image of upper half. So therefore, now this is called plane of symmetry. Now this molecule has plane of symmetry which is optically inactive. Therefore, this is called meso compound, meso tartaric acid, which is optically inactive. Now tell me, there is one important term. It is optically inactive due to what? It is optically inactive due to plane of symmetry, which is also called internal compensation. See how this is. The rotation will be hydrogen to OH, right side. That means half of the molecule rotate PPL to right side. The remaining half of the molecule rotate PPL to left side. H2OH rotation. So, how tane? Right side, left side. So, half of the molecule rotate PPL to right side, remaining half left side. That means the resulting rotation become 0, which is called internal compensation. That means the rotation observed internally, half of right, half left. So therefore, now this is called internal compensation. It is optically inactive due to internal compensation. And of course, plane of symmetry. Wherever plane of symmetry is there, there is an internal compensation, right? Then what is the meso? In generally, now such kind of molecules are called meso compounds. Then what is the meso compound? Meso compounds are, see, the compounds which are having 2 or more chiral carbons. There are 2 chiral carbon. The compounds which are having 2 or more chiral carbon, even though they are optically inactive due to presence of plane of symmetry, called meso compounds. All meso compounds are optically inactive because of plane of symmetry. Okay, now you understood. So what is the criteria for optical activity? The criteria for optical activity is not presence of chiral carbon. It is a chirality, means absence of 3 element of symmetry. Yes, plane of symmetry, center of symmetry, axis of alternating axis of symmetry. If these 3 elements of symmetry is not present, that is optically active. Okay, let down. So take as this meso tartaric acid optically inactive. Write a definition of meso compounds. Meso compounds. The organic compounds which are having 2 or more chiral carbon but optically inactive. 2 or more chiral carbon but optically inactive due to presence of plane of symmetry. Due to presence of plane of symmetry, which is called meso compounds. This is called meso compounds. Next point. Meso compounds are optically inactive. Meso compounds are optically inactive due to internal compensation. Due to internal compensation. Okay, ready? Right? Now tell me, that's it. Last point. Now this is meso compound. Can you write its mirror image? You can write mirror image for any, no? You can take mirror image of anything. Nothing wrong taking. Okay. So what is the mirror image of this? Ide tane? Okay. Now tell me, if these two are mirror images, they should be optically active. The same thing you have studied, no? These two are mirror images of each other. When you get mirror images, when they are optically active, then these two are mirror images. Whether these two are same or different? Now tell me, these two are same or different? If it is same, why you should write D and L? If it is same, you should write DD, no? They are not same. How come same? One can rotate PPL to right side, other can rotate PPL to left side. Now question is whether these two are same or different? If they are different, they are optically active, no? They are same. They are same only. No, let it be both are having plane of symmetry. How to identify whether same or different? This is question. Right. See, if you rotate any molecule 180 degrees, by rotating 180 degrees any molecule, okay, if you get the structures, so by rotating 180 degrees you will get same structures, right? By rotating 180 degrees a molecule you will get always same structure. Now rotate, will you get, this is by rotating 180 degrees. Alright, ಈ ತಲೆ ಕೆಳಗೆ ಮಾಡ್ರಿ, ಕಾಲ್ ಮೇಲೆ ಮಾಡೋದಕ್ಕೆ ಅದು ಬರುತ್ತಾನೆ, right? You'll get it. So these two molecule you'll get by rotating 180 degrees. Therefore, if you get a molecule by rotating 180 degrees, they are called homomers. Homomers means same. Okay, that can be identified by the another concept. The shortcut method is there. I'll tell you, RS nomenclature. Based on RS nomenclature, you can identify whether homomers or not. They are not enantiomers, they are actually homomers. Okay, therefore these two are actually same. Okay.